Hello, hello, hello. 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 Student online. Could you hear me? Hello. Hello. Okay, good. Okay. So, good afternoon, everyone. Time for us to start our class now. So, before I start the class, let me announce something. So, last week, some of you, I think two of you, sent me emails that you want to do consultation on your quiz one. But because at that time, the makeup quiz has not been done, so that OAS cannot retrieve your quiz paper from you because we need to let some other student finish the quiz and then retrieve the quiz paper and do consultation with you. So I think the makeup quiz was done this weekend, last weekend. So that from this Monday, OAS informed me that they will be able to retrieve the quiz paper for you. So that for students who would like to do consultation, okay? Students who would like to do consultation on quiz one, so that please try to send me an email. I will try to schedule a time. I will try to schedule a time for you this Friday. Okay, this Friday. I think for those of you who already sent me, you just wait for my email because I already forwarded email to OAS. I think they will send your quiz paper to me soon. Once I receive it, I will email you regarding the time because I already forwarded your email to OAS. But in case OAS forgot, okay, you haven't received my email by tonight, so tomorrow try to send me an email again so that I will continue chasing an OAS to give me your quiz paper so that we can schedule a time for consultation. Okay, so again, for students who would like to do consultation on quiz 2, okay, if you have not sent me an email now, it's the right time for you to send me an email so that I can ask OAS to retrieve your quiz paper, okay? So for the student who already emailed me, you just wait for my email tonight. If you haven't received, let me know tomorrow morning, okay? I will ask OAS again to retrieve your quiz paper, okay? So good. Now let me share my slides so that we can start our course today. Give me a few minutes, okay? What happened? Okay, so everything works well, so that let's start. Let me start the recording. Okay. Today, we are going to talk about. Sorry. Give me a few minutes. Yeah, but anyway, so doesn't matter. Today we are going to talk about actually chapter 3 and chapter 4 on electromagnetics. Okay, so this is our week 7. So we are going to talk about chapter 3 and chapter 4 on electromagnetics. So this is where quiz 2 will test it too. Okay, quiz 2 will test it chapter 1 to 4 on electromagnetics. That is tutorial 5 to 7. Okay, tutorial 5 to 7. So that quiz 2 will just cover the recent, 3 tutorial material, okay, tutorial material. So today we are just going to talk about chapter 3 and chapter 4, okay. So for chapter 3, we are going to learn another physical quantity, what is called electric potential, okay, electric potential. So what electric potential it is, okay, so it's another, quantity I'm going to introduce today. So up to now, can you recall how many physical quantities we have learned, in electromagnetics until now? Until last week, how many physical quantity, new physical quantity I introduced you? Already 3. Chapter 1, I talk about electric force and electric field, two quantity, okay? Last week, we learned electric flux. So this week, this is also the last physical quantity we are going to learn. So that is electric potential. Okay, that is chapter 3. So chapter 4 is about a capacitor, a circuit element. A circuit element. I think most of you have already been quite familiar with the capacitors. So as you can see, we only have one tutorial question about the capacitor. So most of the time today, I will still talk about chapter 3. Okay, chapter 3. So that first, what electric potential it is? What electric potential it is? So if we put a charged particle inside an electric field, it will experience a certain kind of force. That is electric force. Okay, that is electric force. Then, if you want to move this charge in, the electric field, you must work against the force. So that you can visualize the whole problem like you are in the gravitational field, so that we experience gravity. Then, if you want to climb the stair, you must do work against the gravity, okay? Must do work against the gravity. So this is the same a charge will do in the electric field. If you want to move this charge from point A to B in an electric field, you must also do force or do work against the force. Okay? And the work done from A to B, is what we call a potential energy. The potential energy difference between point A and B. Okay, between point A and B. Okay, so that's the potential energy. As I said, the potential energy UAB just equal to UB minus UA. That is the work we have to do by moving a charge from A to B. So mathematically, this potential energy is a scalar. Mathematically, is equal to minus the electric force. Q log times E is the electric force, okay? Times the displacement vector A to B, from A to B, okay? So why there is a negative sign? So which means, the inner product of A and B. So the inner product between E and the displacement vector AB plus a minus sign, that will give us the potential energy. Okay, the potential energy. As you can see, why we have a minus sign here. So the minus sign means UAB will be positive only when the electric force and the displacement vector are along opposite direction. So for example, if my electric force is point from A to B, okay, so which means Q times E and AB have the same direction, then minus of inner product between two vectors along the same direction will be a negative value. So that if UAB A to B is along the same direction of the electric force, which means my energy is negative. What does this mean? So which means we only need to do negative work against the gravity. So how to virtualize this? You can still virtualize this. Like if we want to move along the direction of the gravity. For example, if we move from upstairs to downstairs, we don't have to do any work, right? Because it's quite easy. It will always be so like water just flow from upstairs to downstairs. Okay, this is the same from higher potential to low potential. But if you want to climb the stair, okay, of course you have to do some work. That will be more difficult. So this is the same. So negative energy, which means we don't have to do any work. It will be quite easy for us to move the charge. Negative energy, which means we have to do work by moving the charge from A to B. So just like we climb the stairs, okay? So that this formula just tell us if, okay, if the force is along the direction of the displacement vector A to B, then we will have negative work corresponding to negative potential energy difference. If the electric force is on the opposite direction of the displacement vector A to B, then we have to do positive work, okay? So of course, this formula is valid for a uniform electric force. If my electric field or the electric force is space dependent, you have to do the integration. Okay, you have to do the integration here. So now you can say the potential energy is actually the charge dependent. Okay, charge dependent. If I have positive charge, the work is positive. Then we switch to negative charge, and then the work will become negative. So right, this is the potential energy. So then the question we would like to ask, can we define a certain quantity similar to the electric field to the electric force? Okay, you can say electric field depending on the polarity of the testing charge. Electric force depends on the polarity of the testing charge, but the electric field doesn't. Then can we define a similar quantity as, for example, to the electric potential, similar as the electric field to the electric force? Yes, we can. That is what we call the potential energy. Oh, sorry, that is what we call the electric potential. The electric potential is equal to the potential energy divided by Q naught. Okay? The electric potential V is equal to the potential energy divided by Q naught. Then this guy will be charge independent. Mathematically, VAB equal to minus E electric field dot the displacement vector AB. So can you tell me VAB is a scalar or vector? In this case, is a scalar or vector? Yes, very good. That should be a scalar because the inner product between two vectors is a scalar. Cross product of two vectors is a vector. Okay, so this is the inner product. So that's why UAB is also a scalar. Okay, so. Again, if my E is along the displacement vector A to B, then we have negative electric potential. So which means if we want to move a positive charge in the electric potential, then we have to do negative. Okay, so this is what the electric potential means. Then if EAB is along the opposite direction of the displacement vector AB, then this guy is positive. Positive potential, which means if we put a positive testing charge inside the electric field, we have to do positive work. Okay, so this is the physical meaning. So that there are three properties we have to bear in mind about the electric potential. First, the electric field. The electric field always point to the decreasing. The electric field always point to the decreasing direction of the electric potential. So for example, if in this case, my electric field is pointed from A to B, it means B will have a potential lower than A. If the electric field is pointed backward from B to A, so now, which means point B should have an electric potential smaller than A. Okay, smaller than A. So the electric field always point to the lower electric potential. This is the first property. Okay. Bear this in mind, what I highlight in red are all very important. So maybe that is what may be tested in quiz 2, okay? Maybe tested in quiz 2, maybe final examination. Then if we take another look at this formula, VAB equal to E minus E dot AB, So can you tell me what will happen if my E and AB are perpendicular to each other? What will happen? What will happen if my E and AB are perpendicular to each other? Yes, very good, because two perpendicular vectors will give us 0. So this means VAB equal to 0, which means my VA equal to VB. If my displacement vector is perpendicular to my electric field, and then VA will equal to VB, there will be no potential difference between point A and B. So actually in space, points with the same potential will form the so-called equal potential surface. So there are two properties about equal potential surface. Okay, equal potential surface. So I think you already learned this. I think in your lab last semester about the electric field. Because what we do to measure electric field is to first measure equal potential surface and then use the measured equal potential surface to construct the electric field, right? This is the lab you did last semester. So the equal potential surface is actually formed by the points with exactly the same electric potential. So again, there are two properties regarding the equal potential surface. So first, on the equal potential surface, the electric field is everywhere normal to the surface. Okay, equal potential surface is always normal to the electric field. So for example, here the electric field should along this direction. This and this always along the surface normal direction. The second property, when we move a charged particle along the equal potential surface, we don't have to do any work. Okay, so which means the charged particle can stay stationary or move at a constant without doing any work. So this is the second property about the equal potential surface. So this figure here shows the some special type of equal potential surface. So for example, if we have a uniform electric field direct from left to the right, then its equal potential surface is given by the dashed line is also this parallel plate. Given by the dashed line. Then the electric field of a point charge element is always along the radial direction. Okay, positive charge from center to infinity, negative charge from infinity back to the center. But the nevertheless is always along the radial direction. So in this case, equal potential surface everywhere perpendicular to the electric field. So that the equal potential surface for the point charge is constant rings. Okay, now. Before I continue, let's take a look at this figure again. Can you rank the potential at the point A, B, and C from highest to the lowest one? Can you rank which one has the highest potential? Point A, B, and C. Use the property I have just talked about. Yes, good. Continue louder. Yes, very good. So for student and team, you can just type your answers on the chat room. Yes, we should choose A. Because electric field always point from higher to lower potential. Okay, so you can say if you compare point A and C, electric field point from A to C. So of course my UA should be larger than UC. Then clearly B and C are on the same equal potential surface. So that my VB and VC should be the same. So what we should run is VA equal to, or VA larger than VC equal to VB. Okay, so if you run VA equal or larger than VC equal to VB. Okay, any question? So no question, let's try this one. So I have to deal with this question under catalytics. I give you 1 minute to choose the answer. Which of the following statements about the equal potential lines or equal potential surface is correct? Which one? So you submit your answer underneath catalytics. Yes, which one? So for students who cannot log in on any catalytics, you can type your answers on so in our chat room. Okay, in our chat room. Ping. So let's look at the answer. So equal potential line equal to charge experience zero force, true or false? True or false? False, of course, because you can say this, take this as an example. On the dashed line is my equal potential surface. Is the charge still experience electric field along the normal direction, okay, along the normal direction. So of course, A is false. So we take a look at this graph, A is false. Then how about B? Electric field is a constant in magnitude and the direction. False or not? In magnitude and the direction. Electric field is constant in magnitude and the direction. On the sine equal potential surface. True or false? False. Give me an opposite example. So for example, the electric potential of a point charge, okay, constant ring. Each point on the equal potential surface, the direction are different. Okay, the direction are different. Okay, this is one example. Okay, so or if you want to say it's not uniform in magnitude, then we can get this is the experiment we did last semester. Okay, we have 2 point charge, one positive, one negative. So for example, at each equal potential surface, the electric field direction and magnitude are different. Direction and magnitude are different. Okay, so C and D, as I said, okay, they are opposite. They are opposite to each other. So again, as I said, equal potential surface is when we move a charge, we don't have to do any work. So that the charge can be stationary on equal potential surface, or the charge can move at a constant speed without doing any force. Okay, without doing any work. We should choose D. Okay, we should choose D. So now let's look at question 1. Oh, okay, any question again? Any question? Any question? So silence means no, okay? So if you have any question, just let me know after the class. We have a uniform electric field of magnitude given by this value, 325. Directed in the negative y direction, okay, in the negative y direction. The coordinate for A, B are given, so C is actually the right angle, so C is also automatically given, okay? So its x coordinate is the same as A minus 2, and the y coordinate is the same as B 0.5, okay? Calculate the electric potential difference, VAC, okay? So which is defined as VA minus VC, then VCB, VCV, C2B, and then determine VAB. So which means this is when we move the point charge from point A to C to B, and then what is the work we have to do, okay? Then comment on the electrical potential A, B, and C, which one is highest, which one is lowest, okay? B, calculate the electrical potential difference VAB by directly using the path. So which means now we want to calculate the work to be done by directly moving the charge from A to B, by moving the charge from A to B, okay? So let's take a look at the 2 parts one by one. So first, VAC, can you tell me, so as I said, electrical potential is equal to minus V dot the displacement vector. So that VAC should be equal to minus V dot AC. Can you tell me what's the angle between AC and the electric field? Looking at this graph, what's the angle between AC and the electric field? Very good, 180, because electric field minus y, AC positive y, so it's 180. So that if you do this minus cosine and 180, it will cancel out the minus sign in front, so that we get a positive value, 260 volts, 260 volts. Then clearly for VCB, I will directly tell you, okay, CB is perpendicular to my electric field, so that the potential should be zero. Okay, the electric potential should be zero. So VA and VC, as I said, VAB equal to VB minus VC, or VB minus VA, so that is equal to VAC plus VCB. Okay, VAC plus VCB. So that we first moving the charge to here, and then from C to B. So that VAB, according to this path, should equal to 260 volts. 260 volts. Okay, so this is the mathematical calculation. Then the question asks us to rank A, B, and C from the highest to the lowest potential. Can you tell me which one has the lowest potential according to this graph? Which one has the lowest electric potential? Electric potential always point from high to low. Lowest electric potential. B and C should be the same because it's on the same equal potential surface. Okay? And then how about C and A? Which one is higher? C higher. Because electric field point from high to low. Right? Electric field point from high to low. So that the electric field point from negative y direction. Okay, so it's from C to A. It point to A, which means VA is smaller. Okay. Okay. Good. Any question? Electric field always point to a lower potential direction.
So, Prof, can we say that with VAC, right? Because VAC, if C is higher with the value V, so VAC you can say just VC minus VA.
Yes, VAC is VC minus VA, that's right. VAC is VC minus VA. So always the ending points potential minus the starting points potential. This is the definition. VAC equal to VC minus VA. Okay? Good? Okay? So that in this case, what we should comment here is my VB equal to VC because they are the same equal potential lines. Then electric field directed from high to low potential. Okay, so that my VB should have the lowest one. BC and B are greater than A. Okay. Then for B, I want to directly calculate VAB by using the path A and B. Then can you tell me what's the angle between displacement vector AB and the electric field E? What's the angle between AB and the electric field E? What's the angle? What's the angle between my electric field or electric field and negative y? What's the angle between negative y direction and AB? Not the positive y direction, okay, negative y direction. Good. So you can say this is theta. Negative y direction is this one. So negative y direction and AB is actually this angle. Is 180 minus pi or minus theta. Okay. 180 minus theta. Okay. Then which means my E dot AB should equal to E times AB times cosine pi minus theta. Cosine pi minus theta equal to minus cosine theta. So this minus from cancel each other. I become E times AB times cosine theta. Okay. You can say AB times cosine theta is directly AC. We get 206. So this question tells us a very important conclusion. So in a certain electric field, if the starting and the ending point are fixed, then the potential difference or the electric potential between these 2 points are fixed. No matter you move it directly, the charge directly along the straight line or along any other curved trajectory, you will end up with the same electric potential. Okay? The electric potential is charge independent. It only depends on the ending and the starting points. No matter you move directly along the straight line from A to B or any other trajectory from A to B, you will end up with the same potential. You have to do the same work. Okay? So this is an important conclusion. Okay? Electric potential is path independent. Let me highlight is path independent. Does not depend on the path taken. Okay? So if in your quiz, the question tell you which of the following statement is correct, and then you said that the electric potential between the 2 points is path independent. Do remember this is correct. You should choose this one. Okay? Okay? So no question. Now let's look at the relation between electric potential and electric field again. So as I said, if electric field is space dependent, then the way for us to calculate the electric potential is to do the integration. Okay, minus E dot ds from point A to B. So that which means given any electric field distribution, we will be able to use this formula to get the electric potential distribution. Then my question is, can we do the other way around? If I give you the distribution of the electric potential, do you think you will be able to get the electric field? Is it possible? Now how? Very good. We should take differentiation, or we should do the gradient. The relation between electric field and electric potential not only given by the integration, okay? So electric field integrate will give us the electric field and electric potential, and then electric potential do differentiation will give us the electric field. So mathematically, the electric field is defined as minus the gradient of the electric potential. So what does the gradient mean? Which means my x component of the electric field is equal to minus dV divided by dx. Y component minus dV divided by dy. Z component equal to minus dV divided by dz. Okay, so you know this is a non-trivial formula because in the quiz, in the final examination, okay, sometimes we will just give you the value of the potential. What you do is to determine each component of the electric field. Okay, so in that case, you don't have to, to apply any complex physics, but you have to, do the math. So what I mean is normally such kind of question will take a lot of mark. So, but just test with some mathematics. Hope every one of you can get 4 marks for that kind of question. Okay, I will come back to this point later. So that this formula is also non-trivial. Okay, it's also non-trivial because it says the electric field is just equal to the slope of the electric potential minus slope of the electric potential. So for example, if I give you the electric potential change with the space, according to this way. So where is the slope equal to 0? For example, at this point, the slope equal to 0. It means the electric field is 0. Okay? Here the slope is negative, which means the electric field is positive or negative. Electric field here should be along positive x or minus x direction. Yes, very good, because slope smaller than 0, minus of it should be larger than 0. So here electric potential should along positive x direction. So here the slope of the potential is positive, minus of it should along negative x direction. Okay, so which means actually the electric field, if we plot the potential distribution on our graph, the slope of this curve will give us, minus slope of that curve will give us the electric field. Okay, we'll get the electric field. Any question? Good. So this is the question I just talked about. I talked about just now. Okay, I gave you the distribution of the electric potential. Want you to determine the x, y, and z component of the resulting electric field. Okay, so actually this kind of question is tested quite often in the or not quite often, but sometimes it was tested. Normally it will take a lot of marks. Okay. As I said, there are no very difficult basic concepts, just some simple mathematics differentiation. Hope every one of you can get 4 marks. So here I will just quickly go through the mathematical solution. Okay, as I said, x, y, and z component take the derivative of v with respect to x, y, and z respectively. Okay, respectively. So that given the electric potential here, the x component is the differentiation of dv. V with respect to x. The first and the second term is not x dependent, so that their x derivative is equal to 0. Okay, so we only take the first derivative of this guy with respect to x. Okay, with respect to x, so that gives an answer. Okay, only one term here, so that you take a look at the mathematics yourself. Okay, so that for ey we do the same. First and the second term goes to 0. Their first derivative goes to 0. The third term, okay, it takes a similar form as x, okay, we just change this x to y, okay, x to y. And then the third term is more complex. Okay, the first of course still goes to 0, but the second term here, we will have a remaining equal to e naught because it's linear dependent on z. Okay, linear dependent on z. And then when you take the third term, both numerator and the denominator is z dependent, so that we have to differentiate the numerator and the denominator, separately, so that we can get the final answer in this way. Okay, try to take a look at the mathematics yourself to see whether you can get a similar answer. Okay, whether you can get a similar answer. Okay, so now let's take a look at some past examination papers. This is a question tested about 2 years ago. So here in a given region of the space, the electric field is given in this way. So where A and B are constant, already given. A and B are constant already given. C is an unknown parameter I want you to determine. So the question gives that the electrical potential Vy equal to 8 when y equal to -2, while V equal to 6 at y equal to 2. Then I want you to determine the constant C and then obtain an expressions for the electrical potential as a function of y. Okay? So this gave us the electric field, want us to determine the potential. So we should do integration or differentiation. Very good. Given the field to get the potential, we have to do integration. Given the potential to do field, we have to do differentiation. Actually, these are the same equivalent. So what we do is integrate E with respect to y. Okay, integrate E with respect to y. But do remember, when you do the integration, of course, this y squared becomes y cubic divided by 3. Y becomes y squared divided by 2. And then the last part becomes 2e to the 2y divided by 2. But do remember, when we do integration, we should put another constant here. Because no matter what constant we put here, the differentiation of this guy will remain unchanged. Okay, you put another constant. Now inside this formula of y, we have now two undetermined coefficients. One is c because a, b are given in the question. One is c. The another one is the constant we introduce. We have two unknown coefficients. But the question already tells us what is the y value, v value at 2y. Okay, for example, v equal to 8 at y equal to -2, v equal to 6 at y minus equal to 2. So that there are two conditions. We will be able to use these two conditions to build up two equations for constant and this is c and this constant. Okay, so for example, substitute v y equal to -2 into this equation. Okay, into this equation. Now we get 8, substitute y equal to 2 into these equations. We get this equal to 6. Okay, this equal to 6. Okay, so now we have two linear equations for c and constant. So that by solving it, we can get c equal to about -0.9 volt per meter, while the constant is about 34 volts. So substitute a, b, c, and the constant into the equation, you can directly get Vy. Okay. I think also quite straightforward. Any question here? Any question? Okay, now let's take a look at, so this is a question tested 4 years ago. So I think it's more or less the same as the tutorial question. I just talk about, give you the value of the, or give you the expression for the electrical potential. I want you now to do differentiation in the field. So that this is not required by our class, so the tutorial. But I already provided a solution here, although I don't have time to go through it. But try to solve it yourself. Okay, try to solve it yourself and compare with my results. So my solution is provided here. Okay. Now, point 2 is the electrical potential due to a point charge. the electric potential due to a point charge. Okay, so that I already talked about the electric potential due to the point charge is concentric rings. So there are another 2 points to be remembered about the electric potential due to a point charge. Okay, so first the V is that scalar. Okay, V is that scalar. Okay, it's not a vector. Okay, second, okay, it's only a function of R. So that mathematically my V is given by the Coulomb formula. My V equal to KEQ divided by R. Okay, now there are 2 differences between the electric field. First is now only divided by R, not R squared. Okay, it's divided by R, not R squared. Okay, second, we no longer have a directional vector, So for electric field is KEQ divided by R squared, and then we have a direction vector along the radial direction. But here V is that scalar, so it's only linearly, it's only inversely proportional to R. Okay, not R squared. So that the final point is my V is always 0 when Q is larger than 0. So V is always smaller than 0 when Q is negative charge. Okay, so here we always assume at infinity the electric potential is there. For point charge, the electric potential at infinity is there. So that minus Q give us negative potential, positive Q give us positive potential. Okay? So this is for a single point charge. Now, if we have a series of point charge, what we do is use this Coulomb formula to calculate, contribution due to individual point charge, and then just sum it up the algebraically. Okay? Just do a linear algebra of the summation for the scalar. And then we will be able to get the total electric potential. Okay, the total electric potential. I have 3 about examples to show how to do that. Okay, so I will come back to this point later. So the last part about this point is what we have talked about just now is an electric potential. Now, if we want to calculate the electric potential energy, we should, use both charge. Okay. For example, the potential energy between 2 charge is Ke times Q1, Q2 divided by R. Okay. By their displacement R. Now, if we have more than 2 charge, okay, for example, 3 charge, and then we have to count how many pairs we have. How many pairs we have? We have 3 charge contains 3 pairs. 1, 2. 1, 3, and 2, 3. And then we need to calculate the potential energy due to individual charge and sum it and then together. Okay? 3 charge from 3 pairs. Okay? Now, my question is, if I have 4 charge, how many pairs I should have? If I have 4 charge, how many pairs I should have? So this is one question, okay, tested in the quiz. I have. Let me see. Why cannot I use pen? Okay, if I have 1 charge, 2nd charge, 3rd charge, 4 charge, how many pairs can this 4 charge form? How many? Very good. That should be 6. This one, for example, 1, 2. 2, 3, 3, 4, 4, 1. We also have these 2, 1, 3, and 2, 4. In total, here we should have 6 pairs. In this case, you need to apply this formula KEQI plus 1 divided by the corresponding displacement vector, corresponding distance, 6 times, and then sum it up all the 6 values together. Okay, so yes, as I said, I will have about 3 questions to show you how to apply these procedures, because I think this is very important. Perhaps the most important about chapter 3, because this was tested really very often in the final evaluations. The potential and the relationship between potential and electric field is important, but just sometimes tested in the final evaluation. But the multiple charge problem, are tested very often. Okay, so here I will, show you 3 examples. Okay, the first one is our tutorial question. Here I have 3 charges on the vertex on the corner of this triangle. Okay, of this triangle. At the top corner, I have 2Q, which is positive, At the bottom 2 points on the base, I have minus Q. So here Q is equal to 10 microcoulomb. I want you to calculate the electrical potential at the middle point of the base. Okay. Then ask you what's the work done by an external agent if I want to bring a minus 10 microcoulomb charge from infinity to the middle point. Then I want you to determine the total potential energy of the whole system. Okay. So let's look at the question A and B one by one. So as I said, at this point, the potential, not the potential energy of the whole system, is the potential at this point. So what we have to do is summing up the potential due to individual charges separately. So the question tells us this length is 4, this length is 2 centimeters. Okay, 2 centimeters. Okay, if we look at this triangle, so the top touch to the basement, okay, to the base is actually by looking at this triangle, use 4 square root 4 square minus 1, so I can get such a length, this length. This is about 3.87 centimeters. So that Ke times Q divided by corresponding R, 2.83 centimeters is 0.0387, okay, in meter. Then these two charges, they are minus Q. Both of them are from a distance 1 centimeter to the middle of the base, so which is 0.01. So substitute the Q into this equation, you can get the final value is about minus 13 megavolt. Okay, minus 13 megavolt. So this is the potential. Okay, the energy, the work we have to do by moving a charge to this point is directly to Q times V. Okay, directly to Q times V. So that you substitute minus 10 microcoulomb into this formula, we get 133 joule. This is the work we have to do by moving an electric charge to this point. So the last question is even easier. Okay, so what we have to do is directly apply this formula, Ke Q1, Q2 divided by the corresponding distance, summing up the 3 pair. Okay, so for the pair and for the leftmost pair, okay, leftmost pair, 2Q and minus Q, so their distance is 0.04 because it's 4 centimeters. Okay, so for the bottom 2 charge, minus Q times minus Q divided by the distance 0.02. Okay, on the rightmost pair, minus Q times 2Q divided by 0.04. Then substitute Ke Q into this equation, I get about minus 44.95 joule. Then what does this minus from me? The whole system has electric energy. So which means if initially the charge at infinity, we don't have to do any work, okay? It will automatically assemble in this pair. Because when they come in closer to each other, the force between them is attractive. So they will automatically come closer and closer to form electric energy. But if this guy is positive, which means if we want to assemble it in this way, to put all the charges together, we have to do force, we have to do work against the repulsive force. Negative energy, which means we don't have to do any work against the attractive force. Okay, negative energy, which means the force between the total force between the 3 particles are attractive. So just like a negative and positive charge, they will automatically each other without us pushing them. But if they are 2 positive charges, we have to push them very hard for them to assemble closer. Okay. So this is the electric, which means the effective force between them is attractive. Okay? Yes, this is a question tested about 3 years ago. Here we again have 3 charges in the right angle, okay, located at the corner of a right angle. I want you to determine the total energy required to assemble all the 3 charges, okay? So as I said, 3 charge, we just need to apply this formula. Use Ke Q1, Q2 divided by the corresponding distance, okay, okay. So the question here gives us 2 distance, for example, the hypotenuse and 1 edge length. But the second edge length is not given. We have to use the Pythagoras principle to get what my R2, 3 it is. Square root 15 square minus 8 square is about 12.7 centimeter. 12.7 centimeter. Okay. Then U equal to KE Q1 Q2 divided by the corresponding distance. We just substitute the individual charge into, for example, the Coulomb's formula divided by their corresponding distance. For example, Q1 Q2 is 8 centimeters, 0.08 meter. Okay. Q1 Q3 is about 0.15 in meter. Okay, then the last one is 0.127, okay, 0.1269 in centimeter. So that we get the total energy here is minus 3.18 joule. Okay, again, this also means the effective force between the three charges is actually effective attraction. Okay, so that is easy for us to understand. We don't have to anymore about the negative repulsive force. Okay. The repulsive in the Coulomb force, okay, is still, this is still a negative one. Any question here? Any question? So for student team, any question? Okay, so no question. Let's look at the last question. Also tested about 3 years ago, but it's for special term, not the the normal term. So here I want you to determine the net electric potential due to 3 charges. Okay, one located at 1 minus 5, the other located at 3 minus 6, the third one located at minus 2, 5. Then the second part is I want you to determine how the electric potential at the same point will change if I set the reference ports not at infinity. So if I set the 0 reference port not at infinity, but corresponding potential at infinity is equal to 10 to the 4th volt, 10 to the 4th volt. Because normally when we apply Coulomb's formula, we assume infinity have a 0 potential. Now if the infinity does not have a 0 potential, what will be the total potential change? So this is what this question asked for. So first, let's look at the first part. Still assuming infinity has 0 potential. So what will it be? So as I said, at this point, the electric potential due to the 3 charge, I just summing up individual, apply Coulomb's formula for individual charge, summing up them together. That's all. Okay. So that for V1 is equal to KEQ divided by the corresponding distance from this point to my Q1. So that this R is equal to square root the x coordinate difference square plus the y coordinate difference square. Okay. So for example, here is 1 minus 4x coordinate difference, then minus 5 minus 6 y coordinate difference. Then I take the square plus them together and then square root. I can get the corresponding distance r. Substitute this value, I can get what V1 it is. Then we repeat the same procedures for V2. So just summing up the coordinate for Q2 here and the 4, 6 for the point we are interested in. So we can get V2. And then V3 repeat the same procedures. We can get V3. Then plus them together, we get about minus 14,3,570 volts. That is the answer for the first part. The second part is okay. Now, this means my reference, my potential at this point is about this value is lower than infinity. Okay, lower than infinity. So infinity, if infinity has a 0 potential, then this is the exact potential at this point. But how about if my infinity has a 10 to the minus or 10 to the minus 4 potential? How my V at this point should change? Yes, very good. Just plus 10 to the 4, because the electron potential does not depend on the path or any reference points. So which means my V minus the potential at infinity should still remain as this value. Okay, which means my mu V minus the potential at infinity should still equal to this value. So that I just use this value plus 10 to the minus 4, then I can get what my potential it is. Okay, new potential is just minus 4,570 volts. Okay, any question?
So you always assume there is an infinity and then your voltage is at 0. Right?
Sorry?
When your potential difference is 0. Like, do you always assume that it's infinity?
Generally, we normally assume at infinity the potential is there.
Oh, okay.
The potential is there. Okay. So that only this will become a Pythagoras formula. This way, the infinity the potential is zero. So if we get, for example, summing up, if you sum it up this way, you get okay, this guy equals 0, which means this point should have a potential the same as infinity. Okay. Good, no problem. So yes, as I said, this kind of question, multiple charge question is quite often. So even in the electric field, we have to calculate the total electric field or electric force for potential the same. So but here I don't have time to look at this question. So again, this is my additional question. Okay, additional question. Not a request by our tutorial. I just show this question to you. I have answered here because I think I have already talked about in depth about this example. I just want to highlight for you this question is very important. Here I have another example. Solution provided. Okay, you can take a look at my solution yourself after the class. Okay, so that I have to jump to another point. So this is what we do for the for multiple charge. If we have charge continuously suppress a certain volume, line, or surface, then we have to do similar as what we do for the continuous charge distribution for the electric field. We have to use this Ke times dq divided by r to get individual segments of this point, and then integrate over the whole volume, the whole surface, or the whole line. So that is what we have to do. Okay. So here I will just use these examples to show you how we could do that. So here I have a rod whose length is L. Total length here is L. With its left end exactly at the origin. Then here is a line charge. Okay, it's a line charge. And then the charge density is actually equal to alpha times x, alpha equal to x. So which means the charge density is gradually increased as a function of x. I want you to calculate the electrical potential at a point A. So again, here we assume infinity has a zero potential, so that we can directly use the Coulomb formula for point charge. Okay. Therefore, determine the electric field Ex along the direction A. So I want you to first calculate the potential and then calculate the electric force. Now let's look at how to do this. So here I give you a summary about how to do the electric potential due to continuous charge distribution. Okay. So what you do first is write down this formula. Divided by whole continuous object into infinitesimal parts, each part du equal to Ke dq divided by r. And I have to write dq as a function of the coordinates. So if it's a line charge distribution, dq equals to lambda times dx. If it's a surface charge distribution, okay, dq equal to sigma surface charge density times dx dy. Volume charge, by dq equal to rho volume charge density times dx dy dz. So this is what we should do for direct dq as a function of x, y, and z. Okay, dx, dy, and dz. And then finally, we integrate du to get u. Okay. So if it's electric field, let me remind you, you cannot directly integrate. You have to decompose your dE into x, y, and z component. Okay, and then integrate each component separately. But for u, because it's a scalar, so that we only need to integrate them scalarly. Okay, so that's enough. So for this question, as I said, as long as you say continuous charge distribution, always write this formula, then you will be awarded already some mark in the final examination. Then, can you tell me this is a line charge, surface charge, or volume charge? According to this graph, it's line charge. Okay. Line charge is then my dq should equal to lambda times dx. Then It's line charge lambda times dx. You write it down, then you will be given some mark again. Okay, some mark again. Then the distance between my points on this segment. Okay, for example, as a segment located at x. Okay, at x, then distance to the point A is d plus this x. Okay, is d plus this x. Then I can write my dv as a sole function of x. Okay, because my r from this point charge to this A is x plus d. Then dv equal to ke times lambda times dx divided by d plus x is my dv. Then lambda is alpha times x. This is what the question tells us. Okay, alpha times dx, I can get dv. Then what you do is integrate this dv from the starting point at x equal to 0 to the ending point at x equal to L. So normally, actually, the integration will be given to you. The integration formula will be provided. So that you just integrate, you find that it's just d plus x minus d log dx. So substitute x equal to 0 and x equal to L into this equation, you can directly get what my v is. This is my v. Okay. So the electric field, we do similar things. We just apply this formula, so it's on x direction. My ke times dq divided by r squared. dq already calculated lambda times dx. R also calculated d plus x. So that you just integrate x divided by d plus x squared. D plus x squared. So when you integrate, these two terms separately, you will find the first term is actually log x. The second term is d divided by d plus x. So at x equal to 0 and L, I can get what my electric field distribution is. Okay. So this is actually how to do the integration to get the potential on the electric field. Any question? Any question?
The dq equals the lambda dx, right?
Yes.
Surface one, then it will be another formula.
Yes, it's sigma times dx and dy, and then you have to do double integration. If it's a volume charge, it's actually rho times dx, dy, and dz. Okay.
So it's more complicated.
Yes, more complicated. But the working case is, as I said, so the integration part is only required in the quiz. I still see it in the final generation. Even in the quiz, I think I only see operate on line charge. I haven't seen it. So although in your lecture, we have some examples about surface charge and volume charge, but I have never seen the surface charge or volume charge tested in the final examination or in the quiz. So in the quiz, I see several questions on line charge. Yeah, so we have several questions on line charge. But in the final, I haven't seen any question on volume and surface charge.
So this is workable.
Sorry?
This question workable.
This is the line charge that will come out.
So it will come out in final test?
No. No, I don't think so.
Also, final test will not have such mathematical calculation.
At least I have never seen. This year I have, so this year I am not putting on, but let me put it this way. This is required, but seldom test, at least in the less than 5 years, has never been tested in the final examination about the integration, even line charge. But the line charge is required in the quiz, because we already have a sample, quite a lot of sample questions. In the database, I'm sure, okay, there are about 10 questions. So out of this 500 to 600 questions, there is about 10 is about integration on line charge. On line charge, okay, about 10. So which means it's still required on the quiz. So that's a lot to say, okay, you don't have any question on this. I can show you one example. Actually. So there is one example. Let me see. Okay, so everyone can see this one. So here we have a charge of uniform density 10 nanocoulomb distributed on x-axis. From x equal to 1.5 to 4 meter. Then the question wants you to calculate what is the electric potential at the origin. Okay, this is one of the quiz questions. So similar to this. So as I said, I would still say the line charge distribution, look at the electric field of potential is still required, at least in the quiz. Okay, at least in the quiz. So every one of you should still try to digest this one. Okay, so let me share the screen back. Okay, so no more question. Let's look at the conductor one. Okay, the conductor one. So sometimes we are interested in knowing the electrical potential on a conductor. The electrical potential on a conductor. So there are two properties you should bear in mind. So first, the electric field inside the conductor is there, and the electric field on the surface of the conductor is always perpendicular to the surface. So we already know if the electric field is perpendicular to the surface, this surface is called what? If the electric field is everywhere perpendicular to the surface, this is what surface? Equal potential surface. Okay? So bear in mind, the surface of the conductor is automatically an equal potential surface. Okay? Is automatically an equal potential surface. Okay? So that there are two properties about the electrical potential of this conductor. So first, its surface is an equal potential surface. The first one. The second one is the electrical potential everywhere inside the conductor core on the surface of the conductor is always a constant. Okay. Inside the conductor is a constant. On the surface of the conductor is also a constant. And this constant are the same. Okay. The whole conductor, the electrical potential is a fixed value. So that here I just give you one example, okay? If you plot the electric field and the electrical potential as a function of the radius r, so you can say outside, the electric field decreases as r squared, while the electrical potential decreases as inversely proportional to r, okay? But inside, something is different. Inside the sphere, the electrical field is zero, okay? You can say the electric field is zero. But the electrical potential is a constant given by Keq divided by R. Why Keq divided by R? Because as I said, the conductor, its volume electrical potential is the same as the surface. The same as the surface. So that if we have this charge uniformly distributed on this spherical conductor, okay, the electric field outside is similar to a charge located at the center. Located at the center. And the applied charge will create a potential at the surface. Just Keq divided by R. Just Keq divided by R. So inside the conductor, the electrical potential is the same as the surface. This is the value of potential at the surface, right? Applied charge will generate an electrical potential just on the surface, the same as in the volume. So that we only need to calculate the electrical potential at the ending point of the conducting surface. We will be able to know the whole potential within the conductor. Okay. As I said, on the surface is similar to a point charge at the center. Okay, so it's Keq divided by R, Keq divided by R. So that now, if in the quiz I give you several plots and ask you to choose which one shows the electrical potential of a spherical conductor, maybe I will give you one of this curve inside the potential is zero. Or maybe I will give you another curve where the potential, inside is not there, but change, for example, gradually increase or gradually decrease. Another curve, the electrical potential is just a constant. Do remember to choose the electrical potential, the constant one, okay, inside the conductor, the same as the surface. This is the electrical potential of a spherical conductor. There is also some quiz question like this one, okay? I give you several plots, ask you to choose which one stands for the electric field for a spherical conductor. Which one specifies the electrical potential for a conductor? Okay, you should understand how to choose, how to make your selection. Okay? Any question? So if no question, let's look at the last tutorial question about question 5. Here we have to charge the spherical conductor. They are connected by a conducting wire. Then I put a total charge I put a total charge 20 microcoulomb, at its combination. So I give you the radius of the two conductors. One is 4, the other is 6 centimeters. I want you to first determine the charge on the conductor and then electric field and the electric potential of each sphere. So that a total charge 20 microcoulomb is given. So if I assume one sphere take charge Q, the other Q1, the other is Q2. So Q1 plus Q2 should equal to 20, of course. But if you want to determine exact value of Q1 and Q2, we need to find another condition. Then what that condition is? That condition is actually due to the electric potential. So then let me ask you a question. If I have two conductors connected by a conducting wire, so the electric potential on conductor 1 and the conductor 2 should be the same rod. If rod, which one should have a larger potential? What do you think? If I have two conductors connected together, whether the electric potential of these two conductors should be the same, or the smaller has the higher or lower potential? Very good. Do remember we should have the same. Why? If their potential are not the same, then on this connecting wire, the two ends will experience different potential, which means we will have a voltage applied across this conducting wire. A voltage applied across the conducting wire, it will always drive the current. Current corresponds to charge flow. So which means if Q1 and Q2 their potential are not the same, and then it will result in current flow in the connecting wire to redistribute the charge. Only when their potential is exactly the same, the charge flow, the current will be there. Okay? So that no matter I have two spheres connected together or multiple spheres connected together, as long as they are connected, their potential will always be the same. This is something you have to bear in mind. Okay, this is something you have to bear in mind. So that here we have two conductors. Once they are connected by an electric wire, potential on them should be the same. So we get what is the electric potential at the surface of the conductor, right? Because if I have a spherical conductor, electric field outside is equivalent to a point charge. A point charge will generate an electric potential on the surface C here, okay, Vc here, equal to Keq divided by the radius. This is the electric potential of a spherical conductor. Okay, no matter on the surface or inside the conductor is the same. So which means the potential only depends on the radius of the sphere as well as the charge on it, okay, the charge on it. So that's according to this formula, because each sphere has different radius, but their potential should be the same, which means my Keq divided by R1, which is V1, should equal to Keq divided by R2, which is V2, okay? So for this formula, I can directly find the ratio between Q1 and Q2 is just the ratio between their radius. I also get another formula, okay, total charge equal to 20. Then I get Q1, Q2 the ratio. I get Q1 plus Q2 the total charge. Two equations just enough for me to solve these two unknown coefficients. I can get Q1 equal to 8, Q2 equal to 12 microcoulombs, okay? 8 and 12 microcoulomb. And then once Q1 and Q2 is determined, okay, if I want to find the field at the surface, I just use Keq divided by R1 square, Keq2 divided by R2 square, I can get the electric field. On the surface, one is about 45 megavolt per meter, the other is 30 megavolt per meter. So again, the electric potential V1 and V2 equal to Keq divided by R1 and Keq2 divided by R2. So both of which are 1.8 megavolt, 1.8 megavolt. So they are the same. So which means our calculation is correct. Because our initial condition is V1 should equal to V2. So that is Q1 and Q2. Now, if what you get V1 and V2 are not the same, which means you have to make some mistake in your calculation. You need to check, okay, you need to check. But now we get V1 to V2, which means our initial condition give us the right results, okay, give us the right results. Any question? Any question? If no, maybe I will spend the last 15 minutes on the capacitor, because capacitor is an electric component, but most of you are already familiar with. So here we only have one tutorial question and one past examinations paper to show you what are the important points. So first, what are the conductor? So ND2 charged conductor, ND2 specific conductor can form a capacitor. What a capacitor mean is we just use the capacitor to store electric charge. Why we need two conductor unconnected? Because we want to store positive charge, the other store negative charge. The one store positive charge, the other store negative charge. They need to be unconnected. Otherwise, if they are connected, the negative charge will neutralize by the positive one. So we have two unconnected conductor, and then we can form a capacitor. One of them can be used to store positive, the other negative charge. Then once we store charge inside the capacitor, a voltage difference will be created between them. A voltage difference will be created between them, and then this will give us to define capacitance of this capacitor. The capacitance between this capacitor. The capacitance is given by the total charge on the capacitor. The total charge on each conductor divided by their potential difference. C equal to Q divided by delta V. Q divided by delta V. So what people found out, actually this C is actually a geometry parameter. It only depends on the geometry of the conductor as well as their separations, but it does not depend on the exact value Q or delta V. This is one important, conclusion. Or to illustrate this, let me show you these examples. From the definition of this capacitance C equal to Q divided by delta V, it directly follows that an uncharged capacitor will have a zero capacitance. Q, of course. Good, which we choose false because C is only a geometry parameter. No matter how Q change, larger Q will give us larger delta V. Smaller Q will give us a smaller delta V, but the ratio between Q and delta V should always remain unchanged. Changing Q or delta V will not change the capacitance. The capacitance only depends on the geometry and the separation between the two conductors. To show you this, here I provide you, some examples of the capacitance due to different capacitors. The first one is two parallel plate capacitor, which is most often used in the electric circuit. We also have this coaxial cable capacitor or concentric spherical shell capacitor. As you can see, the capacity of two parallel plates equal to epsilon naught A divided by B. It only depends on the area of this plate and the separation between them, but does not depend on delta V or Q. So coaxial cable only depends on the length and the inner and outer radius. So that spherical shell conductor, it only depends on the inner and outer radius. All the capacitance is only a function of the geometry. Only a function of the geometry. For our class, we require you to understand the parallel plates. Capacitance is epsilon naught A divided by D. Epsilon naught A divided by D. A is the area, D is the separations. Now let me ask you, if I want to increase the capacitance, how many ways do I have? And what are they? What are them? How many ways do I have to increase the capacitance of my parallel plate capacitor? Very good. What are the two ways? Either increase the area or decrease the saturation. So actually we have a third way, so which I will show you later. A third way. So this formula only shows us two ways. We have another way I will discuss later. Finally, Then the other point is what are the equivalent capacitance of two capacitors in connection. So we can connect the capacitance either parallel or in series. Two capacitors connected in parallel is in this way. Their positive plate connected with positive plate, negative plate connected with negative plate, okay? Then in this case, my equivalent capacitance just equal to the summation between individual capacitance, okay? CEQ equal to CEQ equal to C1 plus C2, okay? Equal to C1 plus C2. In this case, my equivalent capacitance is larger than individual one, So for capacitor connected in series, so which means, for example, my C1 negative plates connected with C2 positive plates, this is capacitor connected in series. In this case, the equivalent capacitance should be calculated in this way: 1 divided by equivalent capacitance equal to 1 divided by C1 plus 1 divided by C2. Okay, plus 1 divided by C2. In this case, my equivalent capacitance is smaller than individual one. Okay, so this is some properties. So the final point about the capacitance is, okay, when we store charge in the capacitor, it will store some electrical energy. So the energy can be calculated in these three ways, okay? Either Q squared divided by 2C, half Q times delta V, or half CV squared. All three ways can help us to get the energy stored in the capacitor, okay? So now let's look at the last tutorial question about the connection of the capacitor, okay? We only have one tutorial question and one partial examination paper to go through, okay? So that let's first take a look at part A. So for this configuration, okay, the middle and the bottom capacitors, okay, for example, the middle two are connected in series, right? So that I use a series connection, I can get my CEQ1 equal to C divided by 2. Then the bottom three also connect in series, so that when I apply capacitor connecting in series, I get C equal to C divided by 3. Then finally, can you tell me the three capacitors here are connected in series or in parallel? The three capacitors here, they are connected in series or parallel? Here should be in series or parallel. Yes? Any answer? The three capacitors here should be connected in series or in parallel. Here, this one. Yes, this should be in parallel, so that we add them all together. I can get, okay, the final answer I had 1.83C. Okay. Then let's look at the second one. So could you tell me first that this C1 and C2 connect in parallel? Hello? 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 Okay, good. Okay, good. So can you tell me C1 and C2, they are connecting in series or in parallel? Very good. C1 and C2 should be connected in series. And then this 2C2 should be connected in parallel. So that we can first get what my ECQ1 and ECQ2 it is. So ECQ1 is just equal to C1, C2 divided by C1 plus C2. I get 3.33 microfarad. And C equal to connect in parallel to C2, I can get what my C equal to it is. And then these three are connecting parallel, directly summing up their capacitance together. I get 8.66. Finally, these two capacitors connect in series. Okay, so apply capacitor connecting in series. I get the final answer as 6.04 microfarad. Okay, so this is a solution for part B. Then for part C is also quite easy. So I want you to first calculate the total equivalent capacitance. The total equivalent capacitance, and then the corresponding charge and energy stored in each capacitor. So that first, let's look at the equivalent capacitance of these two. These two are connected in series or parallel. These two, Very good. Parallel because positive to positive, negative to negative, they are connecting parallel. So total capacitance equal to the summation equal to 110. Oh, sorry, 100 microfarad. 100 microfarad and this guy is connected in series. Okay, connected in series. So that I can apply series connection to get the total capacitance. To get the total capacitance, okay. Once I get the total capacitance, I can get what is the charge across inside the capacitor, okay. The charge applied inside the capacitor. So which is one microfarad, one micron coulomb. Once this Q is given, I will be able to calculate what my delta V1 and delta V2 it is. So delta V1 is 40, delta V2 is 10 volts. Okay. Once I get delta V2 equal to 10 volts, I can use C times 10 delta V2 to get corresponding capacitance. This 40 and 60 microfarad. Okay. So one take about 0.4 microfarad or 400 microfarad. The other is 600 micron coulomb. So once Q is determined, I just use Q squared divided by C, 2C, Q squared divided by 2C to calculate the energy stored in each capacitor. So that's the 25 one corresponding charge is Q equal to 1 millicoulomb. Okay, so this is about 20 millijoule. Okay, 41 is actually the corresponding charge Q1 divided by 2C1, so which is 2 millijoule. The other is 3 millijoule. Okay, so just directly apply the formula. Okay, any question? So no question. So let's look at the last one. So as I said, in order to increase the capacitance between two polar capacitors, we have a third way. The third way is to increase a certain dielectric inside the separation of the two capacitors. So what dielectric it is? Okay, dielectric is any material with refractive index larger than 1. Okay, here we can define a so-called dielectric constant kappa, which is about n squared, the square of the refractive index. And then if we introduce a material with refractive index larger than 1 into this capacitor, okay, and then we will be able to increase its capacitance by kappa, okay, by a degree of kappa. So this is the third way we can enhance or enlarge the capacitance of these power plates, okay, by just insert a material with dielectric constant larger than 1, okay, and then its C will become kappa times C naught, okay, C naught. So the last question here it is we have a power plate capacitor. They are constructed by a glass as the Pyrex glass as a dielectric. Okay, the period glass is a dielectric constant given at 5.6. Okay, 5.6. The capacitance of the capacitor and its operating voltage are both given. Okay, so is 0.5 microfarad and 5,000 volts. Given that the electric field strength inside this dielectric is 14 times 10 to the 6 voltmeter, I want you to determine the plate area A as well as the energy stored in the capacitor. Okay, so first, without looking at the first question, can you directly calculate the energy stored in the capacitor? Can you? We can directly do that, okay? You can say because the voltage is given, capacitance is given, then half CV squared will give us energy. So you can say the second part is actually also directly apply the formula. So it's very easy. The first question is actually more difficult. So this is an example I highlighted when it comes in the final examination. Maybe the second or the third part is much easier than the first one. So you may find the first one very difficult. But as I said, you make sure you go through the question in the end, okay? Maybe the second and the last part will be quite easy. Don't be directly apply the formula, you can directly solve this. Okay, so now let's still look at the question one by one. So that's if we want to calculate for example, the area, which means we need to know capacitance, kappa, under D. So capacitance under D is given. You can say if you rearrange this formula, you get A equal to DC divided by kappa epsilon naught. Epsilon naught is, of course, a constant. Kappa, given in the question, is about 5.6. C is also given, but what remains unknown is D. I need to first get what the separation is before I can get the area. Okay, so in the capacitor, this is one important, a concept you have to understand. The electric field always equal to the corresponding potential divided by the separation E. The question gave us delta V, also gave us an electric field, so that my D should equal to delta V divided by E. Delta V divided by E can give us the separation, which is about 3.57 times 10 to the minus 4 meter. Okay, once I get D, and then all the unknown coefficients inside this formula is given, so that I get my A is about 3.6 square meter. 3.6 square meter. The last part directly use the formula half CV square, as I said. C and V are both given. You can directly get the answer 6.252. Okay. So any question? If no question, this will be the end of the class. Do remember we have consultation session every Friday. Especially for students who would like to consultation on your quiz, send me an email first. I will send you the meeting invitation and then retrieve your quiz paper from OAS so that I can help you go through. But do remember your email to retrieve your quiz paper is mandatory. Okay, so no question, then that will be the end of the class. That will be the end of this class. So for students who have a question, it's the time for you to ask now.
Hello, Prof. Can you hear me?
Yes.
Okay. Can I ask for question 4, right? The electric field. May I ask why can't you differentiate?
Question 4, right?
Yes, correct.
Let's see, 2. Yeah, question 4. Yes.
Yeah. Can I ask for the what's that? The electric field. May I ask why can't you just differentiate the potential?
What?
Can I ask, like, for the electric field, why can't you just differentiate the potential?
Oh, I see. So you want to ask whether it's possible to get the electric field by directly differentiating the potential, right?
Yeah, correct.
Yes, that's right. But in this case, you need to change this D to X. Because you get a potential, you need to derive differentiating the potential with respect to X. Now, this point A is located at minus X, so that you have to change this D to X. And then when you do differentiation with V with respect to this D or this X, then you will be able to get exactly the same answer as this one.
Oh, okay, can.
Yes.
So in this case,
but the way to differentiate is differentiate V with respect to D.
Okay.
Okay.
Yeah, can. So in this case, the D will become negative. X, is it?
So sorry, a little bit. Your arm is a little bit low.
In this case, the D will become negative X, is it?
Sorry.
In this case, the D will become negative X, is it?
So which question?
For the electric field, will D become negative X?
Become what?
You ask me a question of, you just like a reading stand, after that you
because the computer is the voice is quite low. Could you repeat your question?
Hello? In this case, will your D become negative X?
Oh, D become negative. Let me put it this way.
Thank you, bro.
Oh, okay, thank you. Bye-bye. So yes, what you can do is you can set this D, right, this is D, actually is located at x equal to minus D, right? What you want to say is x here should equal to minus D, right?
Yeah, correct.
Yeah, and then in this case, you can assume what you should do is to change minus D to x. Yes.
Mm-hmm. Okay,
you change
can.
minus D to x and then differentiate with respect to x. That's
Okay,
right.
can.
Okay, that's right.
Okay, can. That's all I have. Thank you.
Okay, thank you. No problem.
Yep. Thank you.
Now, how about the other students? Any question? Hello? Yeah, hello? Hello, any question? Daniel Ki Kang, do you have any question? Hello? 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 So if no more question, I will end this session.